A new movie theater with 80 seats has a promotion. The price of a ticket for the 6 p.m. Friday show is 1/10 of the place of the person in the queue to get in. Let k be the index. The place of the person in the queue, which must be an integer, is between 0 and 80. Let a sub k be the ticket price. It is a function of the index, or if you want, a function of the place in the queue. Moreover, a sub k equals k over 10. Let's do here a little chart. Here is the ticket price. For the first one is 1 over 10. For the second person it is 2 over 10. For the third, 3 over 10, and so forth. Here's the place in the queue. As you can see, the first person is paying 1 over 10. The second is paying 2 over 10. The third is paying 3 over 10, and so forth. The last one, the 80s on the queue, is paying 80 over 10. Assume that there were 70 people in the 6 p.m. show. Here is the total ticket sale. It's 1 over 10 plus 2 over 10 plus 3 over 10 plus 70 over 10. We try to write it in a short way. A sub k is the ticket price, which means that A sub k is k over 10. It's the number of the person in the queue, which is k over 10, because the ticket price is 1 over 10, its place in the queue. So this sum is also a sub 1 plus a sub 2 plus a sub 70. And here is the way to express this sum using the sigma notation. Sigma is a shortcut for many pluses. So here it is. It is the sigma when k runs for 1 to 70 of a sub k. As you can see, the lower limit of the sigma is the first one. It's the first index. In this case, it is k equals 1. And the one above the sigma notation is 70. It is the last value for the k. Another way obviously to write it is this, because a sub k is k over 10. Assume that we want to add up all the numbers between 3 to 200. Obviously we can write that. But using the sigma notation, it is really short. It is the sigma of k when k runs from 3, because the first one is 3, and end up at 200. And in this case, the function here, the a sub k, is just k itself. And here's the definition for sigma notation. The sigma of a sub k when k runs from m to n is just the sum of a sub m plus a sub m plus 1 plus a sub m plus 2 plus, and the last one is a sub n. All the a sub m plus 1, etc. are the terms of the sum, and m plus 1, m plus 2, and etc. till n are the indices of the sum. Example. Let's write down this summation. The first index is 8 and the last one is 12. The first term is going to be 8 to the power of 2, because the first index is k equals 8, and what we have to do with this specific index k is to square it to get k to the power of 2. The next one is 9 to the power of 2, because k now equals 9. Then k equals 10, and we have to add 10 to the power of 2. After this, k equals 11, and we have to add 11 to the power of 2. And then we have to add 12 to the power of 2 because k equals 12. But then we notice that we have to stop here because the upper number on the sigma notation, or the last index, is 12. Another example. Let's evaluate the following summation. Sigma of 2k plus 1 when k runs from 3 to 6. The first index is 3. So here is the first term. Now we have to add the next one. So k now equals 4. Now we are going to have another term. This term belongs to the index k equals 5. And the last one is this one. We have to stop here because k equals 6 is the upper index. Now we can do the math and we will get 40. The indices in the sigma can be any letter. Here we took the index to be k. But if k runs from m to n, if you look at the sum itself, you don't see the k anymore. It means that if I will take now the index to be I runs from m to n, I'm going to get exactly the same summation. And also I will get the same summation if I will take the index to be just j. We can conclude then that the index in the sigma can be any letter, because if you look at those three summations, they are exactly the same. Sum whose terms are functions of their indices. It means that the sum is a sum of f of k, and k is the index. It means that you have to sum up some function of the index k. Let's do some examples. In this case, the function is k to the power of 2. We already did this one. And here, the function is 2k plus 1. This one can also be viewed as a function. The constant function of fk equals 2. Properties of sums. The sum of a sub k plus b sub k equals to the sum of a sub k plus the sum of b sub k. Here is the twin for the difference. And here is what you do if you have to sum a constant time a sub k, then this equals to the constant time the sigma of a sub k. If you put all those three properties together, you get the linearity property. Example. I can use now, first of all, that this is the sum of two sums, and then I'm using the constant rule for sums to express the sum of 5 times k as 5 times the sum of k. Now I can also use the fact that the sum of 7 is 7 times the sum of 1. It's very easy to prove the properties of sums. Let's do, for example, this one. The summation of a sub k plus b sub k can be also written as the sum as you can see it. Now I'm using a very simple property that allows me to shuffle the order of the addition. It is okay first to add all the A's and then all the B's. Here are all the A's and here are all the B's. But then, this is exactly first the sum of the A's plus the sum of the B's. And I get easily the first property. With the difference, it's exactly the same thing. This allows me first to add all the A's and then to take away the sum of all the B's. And I get that. For the last property, let's just write it down as it is written. Now we will use distributive rule. And if you look at the bracket, we have the sum of the A's. And we get that.